Hi, everybody. Thank you so much for coming out today. Today's topic is reality is your build target, and we have all the speakers here in the front row. I'm Timoni West from Unity Labs. I'm the director of XR Research. The labs team works on a variety of different projects, but specifically today we're going to be talking about the authoring tools group, which has done a lot of things in the past. These are the projects that we've done. Animation prototypes, using AR as a window into VR, Carte Blanche, Editor XR, Mars, which some of you may have seen it at the keynote. Actually, can you raise your hand if you saw the demo at the keynote? We're trying to figure out if we want to show the video. Almost everyone. Wow, OK. We will not be showing that video then. OK. And we also made a foundational toolkit, which will be coming out later this year. OK, so this is the group. Everyone's shiny faces. Not everyone could be here today. So let's talk a little bit about Project Mars. I'm not going to talk very long, because we want to get into the meat with engineers. But I wanted to talk a little bit about the weirdness that is trying to create for reality. OK, so one of the biggest differences between the way that you create a game today and creating for the real world is that in a game, you know exactly where everything is. You know the actual position down to 10th decimal of every single thing that is in your game. The opposite is true of the real world. Anything could change at any moment. So partially digital worlds, which is to say worlds where you have digital objects that interact with the real world, need to be as flexible as possible, which is the goal of Mars. OK. You need to be able to test a lot, too. Obviously, you can imagine a room like this, and you could probably make a really good experience for a room like this. But try to imagine making that kind of experience work in breakout room number 2 or breakout room number 1. So that was the goal we were going for. Another thing is that the way computers view the world is a weird and esoteric and sort of nascent technology at this stage. So we need to figure out how we can kind of figure out as much about the world as we possibly can now, given really sort of sporadic and incomplete data. Machine learning is really on its way. A lot of it right now is proprietary, though, or dependent on specific types of hardware. So another big problem with world data is often right now, if you have information about the real world, you only get it at runtime on the device. We need to have it in Unity, in Mars, so that you can test and author against it at the time and not have to go out to the real world in order to make sure that your apps work. So this is something we've actually been working on with data providers, is just educating them on how they need to make this data available in the editor. OK, so now those are the big problems, and now I'm going to give it over to Jono Forbes to dive in the details of Mars.
Thanks, Timothy. Thank you, thank you. All right, so hi, I'm Jono. I'm going to talk more about designing for the unpredictable real world and what that means and how we approach this weird problem that Timothy's laid out. And we often talk about this kind of in the context of a few core use cases, because it helps sort of reason about what we're doing here. And the first one we refer to as the sick table jump. And here's our very, very, very first little prototype of a multi-plane experience, kind of pre-Mars, but getting some of the ideas in place, where we set up this experience of like, all right, we got 2 tables and a floor, and I want to do a little car jump over the tables. Cool. Simplest possible multi-plane experience. And that's, like, in essence, what you saw us do on stage, where we have 2 tables and a floor, and we bridge across them, and the character walks across. So obviously, like, much higher production value than that one, but similar setup in terms of the unpredictability. And then kind of a more advanced version of that here we call the Lemmings project. And here we're just showing, however many tables you have, however many surfaces you have, we can build nav mesh against them and incorporate them into the world. So I think here we're tracking 6 or 7 different tables and chairs and stuff. And we have these little nav mesh agents running around them, and you'll see between the tables there are bridges, which are parametrically grown out. So, again, kind of just more complex scenario of the same kind of idea. There we go. You can see some of the other tables down there. And then kind of the next step up for use cases is what I like to call Zeldifying the world, where I want to take a RPG game and plaster my whole world with that game. And at its root, you can think of that as some kind of basic first layer rules, where I'm saying, find the floor and make it water, find anything off the floor, any elevated horizontal surface, and make that grass, and find any vertical surface and make that a wall. Sorry, make that a cliff that my character can climb on. So in that way, kind of from those 3 rules, you already sort of have the entire world covered, and then you can go from there. A more complex scenario yet is one that we talk about of character enters a room, where in this one we say we want a virtual character to walk in through the door of the room, navigate through the room, and sit in an empty chair. So in order to do that, like, we need to know what a door is. We need to know what a chair is. We need to be able to navigate through the room. Like you see, a lot of our demos have pathfinding in them for that reason. So that really gets into this interesting semantic space that we don't really have on any of the platforms yet, but we're very, very close to having that. And then the last one that we talk about, the most complex one, is a cooking helper app, where say I want to have a recipe that an AR app helps me through. And for that, you need really good semantics and really accurate object tracking. So that's like pretty far out still. So one example of semantics that I'm talking about, this is from our friends at Resoneye, and they have this app where you scan your room, it recognizes the objects in the room, replaces them with digital versions of those objects that you can then interact with in VR. But of course, all of this also applies to AR. So that's one example of this kind of like semantic understanding tech that's coming in. So about how we actually build these experiences out. So I'll go back to that Zeldify case again. Like I said, we start with these base layers. Floor is water, tables are grass, walls are mountains. So again, just with that, you get kind of the whole room covered at a basic level. And then you can build out some simple queries where I say, if I find a really big surface, then put this building on it. If I find a really high surface, put a treasure chest up there. You get into these kind of specific scenarios like we were showing in the keynote, where I'm saying, OK, this large and this high. And then you can get into kind of more interesting, relational, more complex queries that you're looking for. So for example, excuse me, in this scene, I have these 3 queries set up. One of them, I'm looking for a couch, or something that kind of resembles the shape of a couch, where I'm like, all right, if I have a floor and then an elevated surface above it and an elevated surface above that, which is probably a couch, doesn't have to be, then put these stairs there. Or if I find 2 surfaces that are at the same height but a little far apart, then put this bridge across. Or 2 surfaces above each other, then put this kind of ending door between them. So that's what I mean when I say kind of more complex scenarios as you build up the stack. And then finally, you can build some really specific, really semantic scenarios where in this example, if I was like, on my fridge, there should be an ice temple, and on my oven, there should be a lava temple. Like, OK, maybe you're not in a kitchen, and you're not going to get those things. So that's why this is kind of the last layer. But you can get into that sort of really, really specific use case. So as a aside here, analytics are going to be a really big deal, continue to be a big deal, be a bigger deal in AR, because I think it's going to be really important for these apps where you're like, probably most players are going to see this content or that content. That kind of feedback is going to be really helpful. Of like, hey, 20% of players saw that lava temple. Maybe you should rethink how you're setting that up. And then that sort of opens the other can of worms of, there's a big question there about data privacy, obviously. When we're talking about AR devices where you're pointing cameras into your living space and at your friends' faces, like there's clearly a big question there for how much data we're able to share and how much we want to share. But I think what we want to be able to do with that once we figure this all out is to be able to give people like a predictor of like, oh, this content you've put in is like 30% likely to show up in most people's spaces, because that'd be really helpful, right? Some other stuff that we're working on that we didn't show yet, of course, marker tracking, right? Obviously, image tracking. As well as 3D markers and geofences. So here in the inspector, I have this condition for this content must exist in Berlin, or like this area of Berlin. So if I was making like a Pokemon Go game, right, I could have a bunch of content that has positional conditions. And then on the left here, what that's representing is a 3D image marker or a 3D object marker. So that's something like you would see from like 6D.ai or PlaceNote, have that kind of tech where you can recognize specific landmarks, specific objects, and place content against them. And something that we kind of mentioned very briefly is fallbacks of, OK, what if I say I need this big, huge surface that I'm going to put my main hero content on, but then I can't find it. Ideally, you'd still be able to have that rule, but say, if I can't find it, then here's a more relaxed rule, or just spawn it in virtually. So thinking in terms of like best case scenario and then how your app gracefully degrades, I think is a key part of thinking about designing complex AR experiences. Idea here, if you're running your app in the middle of a field with no surfaces, then what? So you still got to be able to deal with that case. And procedural content, as I mentioned a couple times, is going to be really, really important for responsive AR layout. So you saw in the keynote, we have this bridge that expands between the two surfaces. Obviously, if those tables were further apart, the bridge would be longer. We also have this prototype that we built that will just fill out every surface you see. So here are some tables, and just for as big as the table is, cover it with grass and rocks and stuff. So I think this kind of like parametric, just fill the world out. Yeah, Kyle doesn't know what's happening to him. This kind of fill the world logic is very, very important for these experiences. And again, nav meshes covering everything, so the alien can jump around. So yeah, in conclusion, parametric content, building up from simplest to most complex cases and being able to handle fallbacks gracefully. And now I'll hand it over to Amy. Thanks.
All right. Thank you, Jono. Hi, everyone. I'm Amy. I work mostly on how the back-end side of Mars integrates with the visual authoring side of Mars. So as Jono talked about, one of the unique challenges of mixed reality creation is making your app adaptable to a variety of spaces. You must make meaningful use of the real world without also being too restrictive. Mars addresses this problem with the construct of conditions. A condition is a component that specifies what state it expects the certain real-world data to be in, with flexible ranges of values for which these conditions can be satisfied. A set of conditions is associated with a Mars entity, which identifies a game object as a part of the whole Mars system. Some conditions are also dependent upon other entities. All right, so let's jump into the editor and take a look at a setup of conditions. So most of our current conditions are spatial conditions, such as checking the distance between two tracked objects or checking the size of a tracked plane. And I want to talk about what it means to author around these spatial conditions and what this implies for how the scene view is used. So as you can see here, Mars provides scene view gizmos that let you adjust these spatial conditions. So plane size, pretty simple, just minimum and maximum sizes. Doesn't depend on any other entities. Distance shows you which entity it is being compared against, as well as the, again, minimum and maximum distances that it can be from that entity. And also notice these transparent arrows here going from this switch to these two platforms. These indicate which entities these conditions are dependent upon. And lastly, some conditions have implicit dependencies. So for example, this elevation condition depends upon the floor implicitly. Now, we need a good way to organize this abstraction of how entities relate to each other and to the real world. So to serve this purpose, whenever you adjust a positional condition, such as elevation or distance, you can see that it is also adjusting the transform of the entity such that it's placed in the middle of these ranges. And you can see that the same applies for distance as well. And the same goes for the other way around as well. If I were to change the transform of this entity, you can see that the elevation is changing along with it. That's what that mouse label is over there. It's kind of hard to see. So the reason for all of this is to not only organize your scene, but to also give you a reasonable idea of how all of your content is spatially related. So in this instance, you can see that that gray platform at runtime is going to be within this range from the red platform. In general, the positioning of entities in a scene is only relevant in the context of the other entities that are related to it. So let's jump back in here. So there's still more complexity to the construct of a Mars scene. A common MR use case is a miniature world, such as the Mars demo scene that you saw at the keynote. Unfortunately, you can't always just scale down your content to support this use case, because systems such as physics and nav meshing will break down at extreme scales. So the solution is to instead scale the parent of the main camera inversely to the scale at which you want your content to appear. This can be hard to grok, so let's take a look at this example. You can see that there's a small phone on the bottom half. That corresponds to the huge phone in the sky in the top half. So the camera parent, in this case the person, is scaled up so that the city appears miniature relative to them. And if you're interested in learning more about why scaling is needed, you should check out Schoen's GDC talk about XR cameras. So in Mars, each scene can specify what camera scale it requires. This is the scene's world scale. AR makes camera scaling even trickier than normal because the digital representation of the real world has to be aligned with the actual real objects in the camera feed. So notice that going from the smaller to the larger world scale, the environment appears to stay the same size, but the tracked plane is taking up more squares, more scene units. It has to in order for that horse, your content, to appear smaller without changing its scale. So when you interpret raw spatial data from reality, that data must be multiplied by the world scale before it is used to drive the positioning of your content. And I'm going to jump back in the editor to show you more about world scale. Let's open up this window here. So in order to see how your content looks relative to the real world, we have to make sure that as you're changing the world scale, the positions of all the entities in the scene, as well as all of the condition gizmos, have to be scaled along with it. Because now a real meter is not equal to a scene meter. And if you look at the inspector as I'm adjusting this world scale, you can see that the plane size condition, none of the conditions are actually changing their values in the inspector. They're all specified in terms of real world scale. So the importance of seeing your content relative to real data really shows here. If we change this world scale back to a value of 1 and go back to this red platform, you can see that this red platform is larger than the minimum plane size that it needs. So as I adjust the world scale up, it takes up less space relative to that minimum size. And you can also see we provide a reference, a real-world object reference to give you a better idea of how your content looks relative to the real world again. Now, to sum all this up, everything I've shown you has involved a lot of implicit adjustment of transforms in the scene. And that may seem strange or counterintuitive at first glance, but it makes sense given how radically different MR authoring is from ordinary 3D authoring. When you're making a completely virtual app, what you see in your scene in the editor is more or less what you're going to see on device. But that's not true for MR. You can't encapsulate all possible real settings in a single scene. MR scene setups must be abstract. What you'll usually end up working with is a bunch of these, what we call digital islands in the void of scene view space. Thanks, Timoni. The positioning of entities is relevant within islands connected by these conditions, but otherwise the world positions are not significant. What's important is that the scene view gives you a sense of how your digital content is related to the real world. And with that, I'm going to hand it off to Stella.
Let me just clip my mic back on. OK, so I'm Stella. I mostly work on runtime integrations and the query backend of Mars. And I want to talk a little under the hood. So as Jono and Amy have shown you, the idea of Mars is really kind of contextual or context-driven authoring. So instead of explicitly designing a virtual scene with explicit layout, you think about the context you need from the real world and lay out your scene based on that. And really, context-driven authoring is data-driven authoring, because the context that you want is given to you as a piece of data. So here you can see the visual representation of two planes in the editor and this sort of debug view that we call the database viewer, where it shows you all of the properties of that. And when you ask for a surface that meets your conditions, what you get back is that piece of data. So you get back, an MR plane with the right pose and the right extents and all that. And each Mars entity defines only the data that it depends on from the real world in order to position itself within the scene. And that's kind of how we drive all of our layout, right? So instead of, we don't allow you to set out all that explicitly. Like Amy showed you how it's all abstract. That's to make sure that you can't even lay out your scene in a rigid way. But there's two more big advantages of data-driven authoring, and one is easier multi-platform support. So you've been able to write a cross-platform AR app in Unity for a while, whether through the old AR interface project or through our new AR Foundation project. But this still involves some writing of code against a common API. You got to go fetch planes. You got to go update your point cloud every frame, check your light estimation, all of that. And in Mars, all of that data comes to you in a standardized format across any platform that can provide it to you. And that is also what enables us to do all of Mars' simulation and testing. Because your scene only depends on that context data, we can fake that context data and simulate. So now I'm going to hop over to the editor and show you some more of that. So I'm going to open up the simulation view here. And as you can see, we have one query that's been matched here. This platform, it has a plane that meets all of its conditions. And these other two haven't been matched. So let's change that. We're going to go over to the pressure pad, and we're going to make these conditions more permissive, right? And now you can see that I've made its elevation range wider, that we've gotten both of these on the same platform, right? Which is kind of a problem for AR, because things can't share space in the physical world. And so you might have heard us say the word query. What we mean when we say the word query is a request for a piece of data about the real world. So your request for this surface data. And when the query is fulfilled, the content is placed, and you see it right here. So how are we going to solve this problem of we've authored these two islands in isolation, and they've both found a match. They both say, this plane meets my conditions. We're going to adjust something called the data exclusivity. which lets us say, actually, we don't want these to share. And so now you can see that we've actually placed this content on 2 different surfaces, simply by saying, don't share space. It's not OK to overlap. And this is a key part of how Mars handles scene layout. So you can author many digital islands at once, independently of each other, without having to worry that other islands will step on your content. So if someone looks at one piece, they don't have to worry about breaking everything. And so I want to hop back to this elevation condition. You heard us say that it depends on the floor implicitly. So judging elevation, you have to know based on what? Based on the floor. And this semantic understanding of what the floor is our big example of sort of filling in the semantic gap that we mentioned earlier. So when you get a plane from ARCore or ARKit, it doesn't have any meaning associated with it. It just has a position and a size. And so we have something called reasoning units or reasoning APIs that run in the background every so often and look at all the data that's available and assign semantic meaning to pieces of it. So the floor reasoning API would go through all of these 5 planes that we have here, and it'd say, oh, what's the lowest one? Is that big enough to be the floor? All right. And then it would tag that piece of data as the floor. And then everything else in our system that depends on knowing its relative elevation, so everything that has an elevation condition, then knows its frame of reference based on that sort of semantic tag. And that system is there to help you fill in the gaps until we reach the AR future where everything is semantically understood. And there's a lot of work that goes on here. All this work of matching real-world contexts, assigning semantic meaning to data, doing your scene layout, it can get pretty complex. And we're doing all of this on mobile devices at runtime. So we've designed the system to take that into account. And I want to talk a bit about performance. So one of the biggest technical challenges with doing a complex experience on a mobile device that lasts for a long time is processor throttling and heat. So here you can see a graph from our mobile performance handbook that shows you how a modern iPhone will throttle down its processor when it gets hot. So around 200 seconds, you can see that we're getting a lot less FPS. So we've designed our system to take these sort of physical, technical constraints into account. And we distribute all of this work of context matching, semantic meaning, across frames and across time. We have a built-in module that makes sure that none of this work happens too much on any given frame. So we'll never cause a frame hitch for you. We'll never slow it down. And you can use the same tech, too. So any custom additions you can make, you can smartly tune performance of them, adjust how often your tasks run, and really emphasize what you care about and what is less important. And our final performance tenet is that we'll only ever allocate managed memory when it's absolutely necessary. And with that, I'm going to hand it off to Schoen.
Thanks, Stella. All right, so my name is Matt Schoen. I'm the integrations lead on Mars, and I'm going to talk to you about the hardware and the software that we have been integrating together to make these augmented reality experiences possible. So here's a really big, complicated matrix with lots of data that you're not really going to be able to absorb, but what I want to call attention to is just the features that we are supporting in Mars, as well as the hardware platforms that we are kind of considering as XR today that we want to think about authoring these experiences against. You'll notice that I've included things like Windows MR, Vive, and Rift, even though you wouldn't think of them as AR, they're still XR devices that we can give understanding of the world, and you got even the Vive Pro here, which is kind of bridging that gap by providing front-facing cameras and world meshing. On top of the hardware platforms, which also have software involved, they're giving you this data, there are individual software platforms that some run on PC, some run on mobile, some run on both, which can give you more world data, which we've been trying to integrate into Mars. So lots and lots of software SDKs, lots and lots of different types of data and ways of accessing the data. How do we get all that together? Well, sorry. I'll talk about that in a second. On top of what we already have, we have room for improvement that we can just do on top of these providers for our use cases. So things like faces, ARKit doesn't give us face landmarks like eyebrows, nose, and mouth, But with that 3D face mesh, we can just extrapolate which triangles are near the nose, near the eyebrows, track those as they move around, and boom, we have landmarks now. Same thing with expressions. Like, am I smiling, am I frowning? There are blend shapes attached to the smile and the frown. Track those blend shapes, and you know whether the person's frowning. So again, it's not something that's provided by ARKit, but magically, there it is. Same thing with sort of interpolating 2D to 3D, getting landmark positions to give us expressions as well. All these things, basically using the data, think about it a little bit, and write some extra code, and then you have more data. Another things that we're trying to do with surfaces, like combine multiple surfaces of the same elevation into one big infinite plane so that we don't have to worry about those little segments that you might get from ARKit, sort of smoothing out all of that stuff, which may not be relevant to your use case, but is still something that you can treat like a first party provided by the hardware piece of data. We've been talking about elevation and floor. That's some more extrapolation we've provided on top. And as well, the rotation, the alignment of these surfaces that you get is not always very reliable, so do some extra reasoning on that, like where is the straight line, or if I don't want my content to face each other, ignore the rotation entirely and just make that happen. Whether the surfaces overlap, don't let them through. And then also a pause button for like, just stop scanning, don't give me any more data, I want my experience to run now. That's all that's all she wrote. So, what I was mentioning before, how do we get all of these things into the software at once, is this pattern called functionality injection. So just a quick show of hands, like who's a programmer who wants to read some code in this room? Okay, decent amount. So if you can read what's on the screen here, you'll see that we have interfaces, base interfaces that provide provider and subscriber identification. Providers are like hardware, subscribers are like gameplay. And we just describe these different features, like you saw in that first slide, the columns of the matrix, as these providers and subscribers. So at the end of this slide here, we have a subscriber for a provider for point clouds. This is what the subscriber looks like. And you notice we have these extension methods here in C# that we use to give your class access to these methods from the provider. So an example would be just a simple point cloud visualizer. It uses point cloud and camera offset to get the scale of the, like Amy was talking about. And then within my class, all I need to do is call this.getPointCloud to get that extension method, and I'm off and running. No boilerplate, no extending another class, no importing more stuff. It's just kind of like you have this functionality for free. I don't care if it came from ARKit or a simulator or the web or something. It's all just going through this one conduit. So these are kind of the puzzle pieces that you can use to put your SDKs together. And you're not talking about Apple's puzzle piece and Google's puzzle piece. You're talking about Mars, only providers that exist within Mars. Here are the provider types that we have so far. It's kind of a long list, but it'll get much longer. A lot of stuff about the camera, stuff about services, marker tracking, light estimation. I put functionality injection here. It's not like a hardware thing, but we also have this, part of the pattern is that we can have a provider of functionality injection that can provide more functionality to more objects that it creates, and it's kind of like just keeps going throughout a loop. So basically, you can always get at every piece of SDK integration at any point in your code base. We also have these hardware providers for the editor, which gets a little weird because, like, what is surface detection on a computer, right? Like, why would I even want to like point my laptop at a plane? But we're trying to get as much as we can to run in edit mode in the editor while you're messing with your scene, so that you don't have to like press play or, God forbid, like build it all and go to your location and have to test and be like, oh, it didn't work. Okay, now I got to come back and do these things. So everything wants to go through the editor as much as possible, because we want this sort of PC to mobile parity. We want to do as much as we can on the PC in exactly the same way that's going to happen in C2. So things like 3D face poses, markerless camera tracking, and surface detection are just kind of like hard to find on a PC platform. But this is why we're trying to make it as extensible and easy to integrate as possible, so that as soon as those things crop up, throw it into Mars and you have your data. So beyond that, when you can't actually get it in the editor, we're also working on a remoting and recording workflow. So instead of going all the way to the place and seeing if it's going to work, you're still in your location, in your actual real-world scene, and you're piping the data back to the editor, and then you can play around with it, look at the inspector, try it again, do all those things, and you're not focused on just this device demo. You have this sort of integrated thing. You could sort of see that going on in the Lemmings video that Jono was playing earlier, where I kind of messed up with the editing, or like moving the editor around, but you saw that the planes from the backyard scene were in the editor, and they're the bridges and all that kind of stuff. So it's useful for local testing. It's useful for field recording of a space. So if I want to have a space that I can mock up and bring into the simulation view, go use a HoloLens or a surface, what are they called, a structure sensor to go and do a 3D scan of my room, And that's my simulation environment. I don't even have to make it up or kind of generate a room. And then also kind of the holy grail is like Jono was talking about, record as much as ethically possible about what's going on in the world, and now we can author against actual real-world situations like a bunch of people milling around in a space or something like that. And then, of course, the fallback is just generate a room with kind of random tweaks and things like that to just see what can we do to really stress test this use case. And now the last thing is kind of a mind-blowing, I don't even know how this really should work, but we have this thing in Mars called iSimulatable, which means that if we put that interface on one of your gameplay classes, we will run that when we simulate it. So part of your game will be running as if it were play mode in the editor in edit mode, and you get to use that to sort of test isolated pieces without having to do your entire gameplay sequence all the way through. I just want to see when I match this plane, something happens. It doesn't matter if that happened first or this happened first or whatever. If I have iSimulatable, we'll take run in edit mode for you, and we'll run your scripts. So we also talked a little bit about reusing APIs already. Just to sort of like clarify or reiterate, they're filling in the missing pieces that the hardware is not providing us. So which surface is the floor? We can use a 2D marker to do relocalization if we don't have things like place note. We can correlate data between two providers. Like I have a face that's detecting my expressions from one piece of software, and I have my 3D head posed on the same physical face, but how do I know those are the same face, right? There's only one face, obviously it's the same one, but these reasoning APIs can help us say that these two separate pieces of data are actually the same piece of real-world data. And obviously more to come. We're interested to see what you guys can come up with, and that's pretty much it. So we have a little time for Q&A. If you guys want to come up to the mics, yeah, just so we can hear you on the stream. And I guess if you guys want to come up too, so we can all answer questions. Yeah.
The last part is very fascinating. There's a company called Affectiva, which does emotion-based analytics, and they have some patents for emotion-based gaming.
Cool.
And I wonder how this matches with what you are doing. So if I say I detect an emotion in a face, will they sue me because I infringed their patent, or are you aware of that?
So yeah, so they would be it's not in this list. Oh yeah, a facial expressions provider.
Yeah.
And perhaps they would even define a new type of data, which is like a emotional state or something like that, right? Because expressions are like smiling and frowning, not like happy and sad. But so that the way that we're parceling this out is like, what is the actual data that you're providing? Can I make it conform to an existing interface, or is this like a new type of thing? But essentially what they would do is you would just have a wrapper on their SDK that then implemented whatever providers you could provide, and Mars will pick it up and integrate it and use that as a data source. So yeah, you should put us in touch. It sounds really interesting, and we'd love to integrate that. What was the company name again?
Affectiva.
Affectiva, yeah, we'd love to have Affectiva provider.
The largest emotion database in the world with millions of faces, and they do it with AI as well.
Cool.
So, yeah.
Cool. Awesome.
Okay.
Thanks. Anyone else?
Hey, I'm a little confused right now. A lot of information in the morning.
There's a lot of information.
Yeah.
What is Mars and what is AR Foundation? How do they compare?
Okay, so Mars stands for Mixed and Augmented Reality Studio. It's the same thing we announced at the keynote. AR Foundation is a package you can use in 2018 to do cross-platform AR development without pulling in an additional SDK.
So AR Foundation is kind of a plane finding provider. We're using we will be using AR Foundation as the way to talk to ARKit and AR Core, and then still kind of funneling that in through these provider interfaces to Mars. So they're both related or both involved. But Mars is a authoring toolkit for making experiences. AR Foundation is more of a SDK integration.
Okay, thanks.
Thank you.
How do you guys plan to deploy it? As in, is it going to come with the editor, or it will come as a package again, and you add it on top of AR Foundation?
It'll be a package.
Package, yeah.
Yep.
More or less TBD, but package probably.
Yeah, package.
It's also very early in this project too, right? This is the first time we're showing it. This is like first anyone's ever really hearing about it. So if you're confused, don't feel like you're out of the loop or anything.
Yeah, again, this is a lot of information in the morning, so thank you for sticking with us.
Yeah.
Hi. Are you going to build a database of simulation environments taken from the real world? So
Yes.
like Anonymous, you can check how many people would able to play the specific app?
Yeah.
Yeah. So right now, I'll get this thing on. Right now, we just have a set of environments that you can try against. That's what you saw in the keynote, just kind of clipping through. But then Schoen mentioned also we'll be working on a room generator, so just kind of make randomized generated spaces. And then what I was mentioning about, there's the whole question of like, how much do people want to share their spaces, but as much as people are comfortable sharing their spaces, we would love to have kind of here's a database of like, here's kind of what my apartment looks like, and here's kind of what the office looks like, and you can use these as examples to try against. So yeah, the hope is that that'll just ever grow with more content to simulate against.
Cool.
Anything else? Oh, yeah, one more.
One more.
Hi. In the keynote, it showed an example of the character walking across the table on the bridge. You mentioned using the reserved constraint to stop the two things appearing in the same space. Am I right in understanding that that was actually a couple of things appearing in the same space, and how was the reserved thing used there?
So those are actually two different surfaces, two different islands as we were describing them. And the bridge was a connection between the two, but it wasn't a fixed piece of content. It was actually two separate things. The tables could have sort of been in any orientation. We were trying to keep it as controlled as we could. But yeah, the two platforms that the character ran between were as if they were that pressure pad and platform. They were separate components that are separate objects that we place on the surfaces.
So the
Each
character
surface
was
reserves its own space, and then the bridge is actually an off-mesh link in nav-mesh. So it's,
Right.
yeah.
Okay. And the character was actually part of
one of the surfaces, yeah.
Okay, right.
Yeah.
So character and ground were one unit essentially.
Mm-hmm. Yeah, and that also does, we can mock up in the editor. Here's how big the character is going to be. Here, is our simulated version of the stage and how far apart they can be. And yeah, all of those things can still be sort of visualized in the editor, even though it might change in reality. Thanks.
All right. Anybody else?
I don't know how we are on time, so.
All right.
All right.
Thanks everybody.
Thank you.